So those are our learning goals. We'll start out with the electromagnetic spectrum and make sure that you're all comfortable with this. Um, Electromagnetic radiation is any form of radiant energy within this electromagnetic spectrum. And you see some of the names here, and you're familiar with some of these names: microwaves, ultraviolet, X-rays, radio waves. Okay, and there's your kind of visible light in the middle. There's other ones that are missing here, but you can add more things. There's all different sorts of waves that we use for cell towers and stuff like that. There's cosmic rays, but this just gives you an idea. And we also have a couple other things here. We've got the frequency and we've got the wavelengths. So here's the wavelength in meters. You can see there it's in meters. Okay. And as we move from left to right, that wavelength is increasing. So over here it's 10 to the fourth, and down here it's 10 to the minus 16. Okay, so wavelength is increasing as we go to the right, which means that, gamma rays, that's the gamma symbol, Greek symbol gamma, that's one of the forms of radioactive energy that we talked about, alpha and beta, and I think I mentioned gamma briefly. Gamma is not a particle, it's a wave. Alpha and beta are particles. So when we think about waves, we think about something that, doesn't really have a position. You think about it just spreads into space. When you think about the light above your head or something like that, it's just a wave. It moves, and we'll talk about that in the next slide. It moves through space by propagating its energy. Okay, so we've got, long wavelength, large wavelength stuff like radio waves, and very small wavelength gamma rays. And then we also have the hertz, which is the frequency. This is hertz, and you might know that from music or from sound. And hertz, the units of hertz are seconds to the minus 1, so it's the same as saying 1 over seconds. And kind of like what we say, it's like oscillations per second, but oscillations is not really a unit that's going to work with mathematical equations and cancel out. So it's really just per second, but you can call it as oscillations per second. That's what a hertz is. Okay, and that's what it is. It's the number of oscillations the wave makes in a given second. And that's going to be the opposite, you'll notice, of the frequency, and that is the high frequencies are over here, right? 10 to the 24th on this end. And over here, we've got down to 10 to the 4th. So when the wavelength increases, the frequency decreases, and vice versa. So they're inversely proportional. Okay, and the visible is right in the middle there. You see it. And you'll notice that ultraviolet borders right next to violet in the visible spectrum. There's ultraviolet. And infrared borders right next to red of that visible portion of the spectrum. And the violet end is the smaller frequency and therefore, smaller wavelength and therefore higher frequency, right? 400. So visible spectrum, people usually say is about 400 to 750 nanometers. Okay, so 10 to the minus 9 meters there. So it'd be 400 times 10 to the minus 9 to 750 times 10 to the minus 9 meters. So that's the electromagnetic spectrum. I think that's really what I want to say as we move on and talk about the waves a little bit more. This is how they propagate through space. So if your friend has one end of the rope and you have the other and you flap it, what happens? Well, the energy of your motion of your hand travels down that rope, right? And it forms like a bit of a sine curve. That's the energy propagating. So it's not the actual movement forward of any matter. I mean, yes, the rope goes up and down, but it doesn't move from your friend's hand to your hand. The energy moves through the rope and causes the matter that it's propagating through to oscillate, but it doesn't really move forward. Okay, so that's the little bit of an abstractness of what waves are. When we think about particles, they're easy to define, but waves are a little bit more difficult. So the wavelength is the distance from a point on one wave to the same point on another wave. So it could be from crest to crest like here, but you can measure from trough to trough. It will be the same. So that's the idea. So a complete wave then would be something like this. Let's use a different color here. Complete wave would be, boom. That would be a complete wave. From the starting point to at the axis to to there, or you could do it from here. You could do it from where you want, but that would be a complete wave right there. Okay, um, so we can shift it, if you will, and you get your wavelength here to here by shifting it and saying the complete wave there is from here to here. So you can measure it any way you want, or from here to here. All right, so wavelength B, as you can see, is less than wavelength A. It's got a shorter wavelength. So lambda is the symbol for wavelength. Okay, that's the Greek symbol lambda. And frequency is this Greek symbol nu, it's called. It looks like a cursive V. And we'll notice the relationship here, c equals lambda nu, where c is the speed of light. When we talk about Einstein's equation, E equals mc squared. This is the c. This is the speed of light, 186,000 miles per second, or 3 times 10 to the 8th meters per second. That is constant. All of these are traveling at the speed of light. Our sun gives off the entire electromagnetic spectrum. Not all of it reaches Earth, but it gives off the entire electromagnetic spectrum. It doesn't give off a ton of radio waves or a ton of gamma rays. It gives off a lot more ultraviolet, infrared, microwave in that region. But nonetheless, it gives off the entire spectrum, and they all travel at 3 times 10 to the 8 meters per second. That is the speed that light travels in a vacuum. It changes if it travels through air, changes if it travels through water. It doesn't change that much through air. It's a small change. Okay, so this is a constant, which means that the product of these two always has to be the same. And that makes sense because we said that as the wavelength increases, the frequency decreases. They're inversely proportional. So as one increases, the other has to decrease because the product always has to be this. Okay, the amplitude, I don't know if your book talks about it much. You're not really responsible for it, but it's basically the energy of the wave as measured by its height. You think about when you think about water waves, larger waves have more energy. It's carrying more matter, if you will. But we're going to find energy in a different sense in a bit here. But that's really, when you think about water waves, that amplitude, things like that, is that amount of matter. It carries much more energy. All right. So, now, people always thought of the sun, early scientists, as having a continuous spectrum. Okay? Then people started to get better instruments and better spectroscopes and started to look at light a little bit closer and realized actually there was a bunch of dark lines. So it wasn't truly a continuous spectrum. Okay, so the question is, well, what's going on? Why are there all these black lines? Well, additional work was being done, and scientists were looking at things like, excited atoms in the gas phase, stuff like that. And they noticed that, for particular elements, you would see bright lines in a spectrum. So if I excited like hydrogen gas within a tube, it would give off light, and it would give off specific bands of light, frequencies of light. But then if I also did an experiment where I had light source, and I'll just draw, I can't draw for the life of me. I'm terrible. That's my light bulb, my light source. If I pass light through a tube of, say, hydrogen gas, it absorbs. That's what we call an absorption spectrum. And instead of what you see over here being a continuous spectrum, you see this. So this is an absorption spectra. And the emission is if I take hydrogen and I excite it with a voltage, it gives off this. So this is the emission spectra of hydrogen. And I think this is hydrogen. I'm not positive. Yes, that looks like hydrogen. But it could be any element. would just want to be the same in both cases. Hydrogen, hydrogen, helium, helium, whatever. These lines here correspond to the black lines here. So basically, the bright lines in the emission spectra and the dark lines in the absorption spectra of elements correspond to each other. So the idea, what we were realizing here, was that the reason you don't see a continuous spectrum from the sun is because all the elements that are in the gaseous phase around the sun's, corona, it's burning there, right? It's a big fusion reactor. All those are absorbing frequencies of light. So when we see it through the spectroscope, we see a bunch of black lines if you have a good enough spectroscope. All right, so this is something that's a little bit advanced and beyond this course, but we need to introduce the idea here. It's something called the ultraviolet catastrophe. And basically, it was a particular scientist studied the spectra of sources of radiant energy called black body radiators, which are perfect absorbers of light when cold and perfect radiators of light when hot. So it's kind of like putting a poker in a fire, okay, and it glows. Well, all I really want to say here, and then you can see different colors in that it glows based on the temperature. You can read this in your book. All I really want to say is that classical physics was unable to explain the relationship between temperature and the emission of light. And they call it the ultraviolet catastrophe because of this drop-off here. That's something classical physics wouldn't have predicted at all. Classical physics would have predicted something like this, where the higher the temperature, you keep getting a higher frequency of light given off, more energy. So it makes sense. Higher the temperature, I heat that piece of metal in the fire, the smaller the wavelength, the greater the frequency of light given off. That's not the case. That's not what happens. And classical physics could not explain that. So Max Planck is really the first giant of quantum theory. And he proposed that objects emit electromagnetic radiation in integral multiples of an elementary unit. That's the idea of a quanta or quantum. Okay? A quantum of energy. Okay? And he comes up with this famous equation. This is Planck's equation right here, E equals h nu. And of course, since we know C equals lambda nu, you can do a substitution and get this equation here. But what this equation is, it's the energy of a single photon or a single quantum of electromagnetic radiation for a given frequency. So let's say I have infrared light. Or let's say I have red light, to make it simple, in our electromagnetic spectrum. So it's around 720 nanometers. That would be on the red end of the spectrum. So let's say I have something like this, right? Right here. Okay? Whatever that frequency is, that corresponds to that wavelength, because we can put in the wavelength here. We know what this is. We can solve for the frequency. Put that frequency in here with this constant. This is a constant right here. So it's the same all the time, Planck's constant. That's the energy of a single quantum of that light. And we now call these photons. They are the particles that make up light, if you will. So you're starting to see the beginning of quantum theory saying, hey, light has particle characteristics. Okay, so this is the energy, remember, of a single photon. So the number will be real small when you calculate it. If you want to know the energy of a mole of photons, we'll just multiply by Avogadro's number. Okay? So the idea here was that energy is given off in like these discrete packets. And this idea of quantum is kind of like steps. So the best analogy that's used typically is thinking like steps. Like lots of things in nature are quantized that don't have continuous infinite possibilities. For instance, you can give birth to 1 or 2 or 3 or 4 dogs, children, lizards, whatever. You can't give birth to 1.1. Those are discrete. Piano keys are discrete. You press on one key, you press on another. There's nothing in between that. All right? Steps, that's the whole idea. You're walking up the steps. You either have enough money, you either have enough energy to pick up your leg to go to the next step, or you don't. You can't go partially with some of the energy and then save up the energy and go the rest of the way or something. That you can't do that. That's the idea of it being quantized. So Bohr, what he's saying, or Planck, what he's saying here in a sense, is that the energy of these waves is quantized. And that, it's a little bit beyond what we're able to look at in terms of math and explanations, but it helps to explain this right here. Okay? So, what Einstein does now, he explains what's going on with what's called the photoelectric effect. And the photoelectric effect is when electromagnetic radiation hits a metal surface, and the metals then emit electrons. And we use this all the time. Any sort of solar type of powered thing, any sort of kind of electronic like door opener that senses, like when you walk into the supermarket and the door opens up for you, that works on the idea of the photoelectric effect. Okay? Is that you're blocking the light. When the light's shining on the metal, it keeps the door closed. You walk in front of it and block it. That forces the switch to open up. So it's kind of a reverse switch of what you would think about. So that's what this is showing you. This metal surface shines, and we get this movement of electrons, okay, that comes off the surface. Well, what's interesting then is the fact that it requires a certain frequency to get the electron to move, which means basically that it doesn't matter how intense the light is, I can shine. Intensity is kind of like the density of the photons. You can make a super intense laser, you can cut through metal, Einstein basically showed and proved that intensity doesn't matter. It's the frequency. So his summation was to use Planck's idea. So here's my atoms within my metal, and they have electrons associated with them. It doesn't matter how intense the light coming in is, it has to be the right frequency. It's kind of like if you have a nail sitting in a piece of wood, okay? And you just lazily tap with a small hammer, and the nail doesn't move. And you could do that 1,000,000 times. The nail will never go in the wood. Why? Because none of the strikes have enough energy to move the nail. So same thing here. You have to have the correct frequency to get the electron moving. This is not what classical physics would have predicted. It would have said, I can get the electron moving. I just can use more intense light. This uses the idea of quanta and that they have a particular quantum of energy associated with them that's needed to come over this threshold. So the way Einstein described it is like, imagine, the electrons are embedded in this glue. And you have to have a certain amount of energy to knock it out of that glue. And that energy is dictated by the frequency, not by the intensity. So you can imagine a photon has to hit the electron and knock it out. So this gets to the idea that wave has particle characteristics, because if it was wave-only characteristics, you would say, well, the electron will just keep absorbing that wave until there's enough energy to bounce off of the glue that he's talking about. But no, that's not the case. It's individual photons that are bombarding it. So a photon has to have the correct energy to dislodge it, and that's the key. So we take this further now and start to explain these lines that we were seeing earlier. And don't worry so much about this equation. You can read about it in your book. But it's empirical, which means just coming up with an equation to describe what you see without knowing anything about theory. So the idea is he could predict the wavelength, and you can read in your book, I think in this case, N1 had to be greater than N2, and they're integers, and one of them had to be equal to something else or something. You can read it, because all these equations got so many different forms, different scientists changing it. But he was able to predict these 4 lines. the equation that becomes important, so you have people like Rydberg and other people that worked on this. I can't think of their names. But ultimately, Bohr comes along, and his equation we'll see in class is going to be a modified version of this. And here it is here, but we're going to look at one that's a little bit different, where it looks at electron transitions. He comes up with this orbital theory. This is the planetary model of the atom now that you all learn. The nucleus in the center, then you have these fixed orbitals of energy where the electron resides. There is no electrons that can reside in between the orbitals. This ties into this whole idea of this quantum steps that plays into the idea of electrons interacting with light and electromagnetic radiation as a particle-particle interaction, and the particles of light, those photons, have to have enough energy to dislodge it from this particular energy level or this particular energy level. And the intensity of light doesn't matter. So there's these fixed orbits around the atoms. That moves us on from the plum pudding model and then the modified plum pudding model with the nucleus in the center, fixing the electrons in these fixed orbits around the nucleus. And then Bohr's model, he was able to show these are the 4 lines right here that you see in the hydrogen spectra right here. He was able to explain these as electronic transitions. So what we'll learn about in class, and is that electrons will emit light energy, electromagnetic radiation, when they go from a higher energy state to a lower, and they absorb energy when they go from a lower to a higher. So initially they'll absorb energy. In this case, this is ionization. It's completely being removed from the hydrogen atom. But if it's not completely removed, it's absorbing. That's the absorption spectrum, right? Emission is when it comes back down to a lower energy state. It gives off light. Bohr's model explained those 4 lines as transitions, and specifically transitions from these different orbits around the atom, different energy levels. Ultimately, we coming full circle to the idea that electrons, which are particles, we've always thought, have wave characteristics. They're behaving like waves the same way light, which is a wave, has particle characteristics. This is the wave-particle duality that we talk about. So electron has both particle and wave characteristics, and electromagnetic radiation has particle and wave characteristics. Particles are the photons. Waves is that, when we say waves, it can be reflected, diffracted, right? Refracted. Electrons are the same. They can do all of that, but they're also particles. And what this figure shows is the difference between a light microscope and an electron microscope. Light microscope are the top 2 figures, and the electron microscopes are the bottom 2 figures. The resolution that you get from a microscope is dependent on the wavelength. The smaller the wavelength, the way to think about it, it's not that simple, but you can say the smaller the wavelength, the more it interacts with the matter. So radio waves don't interact much at all with matter. Hence, we can pick up a radio signal from inside our car and inside our house. It can pass through walls. It can pass through, right? Smaller wavelengths have a little bit more interaction, you could say. That's not entirely accurate. I hate to use this analogy. But anyway, so you get better resolution. Let's just leave it at that. You get better resolution the smaller the wavelength. Okay? And it has to do more with interference and stuff like that. So this is a light microscope, and this is an electron microscope. Light microscope, electron microscope. The electron's wavelength is much smaller than the wavelength of visible light. And skipping a lot of the intermittent quantum theory and getting to kind of more the end point, sort of, not the end point, but we'll define this wave function. Schrodinger will do that. And ultimately, they'll mathematically realize that the square of that function gives you a 3-dimensional region in which you can predict the probability of an electron. And you can define that region however you want. You could say, okay, I want to know the small region around the nucleus where the electron spends 10% of its time. Or I want to know where the electron spends 90% of its time. You can define that mathematically. And that's what these dots are. And this is meant to show a probability sphere. And I don't know, this is just a schematic, whether that's a 90% probability or what, where the electron resides. This, of course, is not an electron. It's just a spray, an atomized spray here. So that's what we do. We talk about the electron's probability of being somewhere because it's like light. You can't pinpoint so clearly its position, and we'll talk about that more in class. So ultimately, what comes out of all of this is the ability to actually define electrons within specific orbitals in atoms, giving them electron configurations and defining the regions in which they reside, so we can figure out, hey, which electrons are mobile, which ones come off when you do this, which ones cause bonding. Allows us to explain a lot. And one of the things we can explain is trends that we see on the periodic table. And one of the simple ones is simply atomic size. And you can explain that simply using the Bohr model of the atom, that the more energy levels you have as you move down the periodic table, this refers to these quantum orbital levels that we see here, right here, the larger the atom. So you see an increase in atomic size as you go down the periodic table. That can be explained by the understanding of quantum theory, and that's one of the conclusions we'll get out of this. With that, I'd like to conclude the video.